Hello, everyone. Thank you for having me today. My name is Ali Khosravi, a research associate at Oregon State University. I'm working with Dr. Hutchings on the topic of mechanics of sea ice at small scales. When talking about sea ice mechanics and its consequences involve a huge range of scales, spatial and time scales. Spatial scales ranging from individual flow all the way to sea ice cover, and time scales ranging from seconds to years. And then we have, of course, fracturing and crushing of saline ice against offshore structures and ship hulls that include even smaller scales, the internal microstructural scales. Understanding of this scale, I believe, is something necessary to estimate ice load to these types of structure. Over the years, there have been many approaches developed for modeling of sea ice at different scales. Depending on the scale, we have continuum-based models, mostly for pack ice scales or for climate models where larger scales are concerned. And then we have discrete element models that are used for smaller scales where the discontinuous nature of the sea ice cannot be ignored. These discrete element models especially have been used for modeling of sea ice at the scale of lab and field tests, especially like unconfined compressive tests or borehole jack tests, result of which have been used for different applications, like to better understanding of the mechanics of the sea ice at these scales, or even for the calibration of larger scales models. And my focus in this presentation is going to be at this scale, on the sea ice at this scale. Here you can see the configuration of the sea ice we usually have at this scale for element scale and for a borehole jack test, and the procedure for the modeling of sea ice at this scale is pretty much like what you can see here. You have discrete particles connected together with some simple contact models that have some properties, some shear stiffness, strength parameters, some density parameters, and some friction, angularity coefficients involved. Then we have material definition that is determined based on the type of sea ice we're dealing with, the arrangement. We have model calibration, which is a process performed by comparison of the numerical simulation of an element scale test, unconfined compressive mostly with real experiments. And then we have validation process using the calibrated model parameters for a larger scale experiment. Here you can see an example of an element scale model using DEM presented by G et al. In 2017. You can see the particle arrangement and the particle geometry, and you can see how the model captures the response of the sea ice in terms of strength, strain, and in terms of the fracturing pattern. And from this, you can say, yeah, it's able to do good in terms of strength and fracturing. But if we look at the assumptions, we will see there are some issues with these simulations. Here are the assumptions we have for these types of studies. We have particles that are mostly spherical, single size, arranged in an hexagonal way, and the model they use usually for these types of simulation is parallel bond. What are the issues with these assumptions? Let's start with the spherical particles. With the spherical shapes for the particles, we're going to miss two of the main characteristics of a granular material. Angularity, and with angularity here, let's say first, this is what we have in simulations. This is what we have in reality. No angularity after bond breakage, as you can see here. If there is no angularity after the bond breakage, then the behavior we are going to have in the post-failure range is going to be considerably different to what really happens in the field. Then we have friction. What usually considered in most of this simulation is some random value with no consideration of the conditions involved, but we all know that internal friction in sea ice is going to be affected by different parameters, different conditions, especially temperature and the particle arrangement. So if we don't consider them in our simulations, again, results are not going to be accurate. We go to single size and hexagonally arrangement assumption of these models. This is what is assumed, but in real condition in the CIs, we know that there is a complex microstructure for the CIs. We have different arrangement of particles. We have granular or snow ice due to the position and subsequent consolidation of snow. We have fragile ice grains nucleating in fast moving area, and then we have columnar grain structure and aligned CIs happening when an ice plate formed on a standing body of water. Different arrangement, if not considered in simulations, results again are not going to be accurate. And then we have, due to these different arrangements, we have a complex sets of boundaries, grain boundaries, and some pockets of brine and channels. And with all this, we're going to have some micro cracks in the CIs, and micro cracks are going to affect the response of the CIs significantly. Again, if not considered, that are usually not considered, they're going to result in erroneous conclusions. About parallel bond model, one of the conceptual assumptions we have in these types of model is that the shear strength of the bond is a constant value independent of the normal stress. So for the condition which is unconfined compressing, the compression condition, this can be a fair assumption. However, in reality, we know that CIS is under different confinement conditions, and then we know that shear strength before bond breakage or after bond breakage is going to be a function of normal stress. Then we have confinement. As I mentioned, most of these tests are performed under an unconfined compression condition. But in reality, this is just a special case we're going to have. CIS is going to be under different confinement conditions, semi-confined, fully confined, or even triaxial state. And if we don't consider these confinement conditions, the behavior we're going to have in reality is not going to be captured. At lower confinement, of course, the crushed ice is able to expel more easily when reaching or during ice structure interaction. That means we're going to have lower failure pressure. In terms of behavior, we're going to have both brittle and ductile behavior at low confinement, but then, under confinement, the behavior is more toward a ductile behavior. Then about the strain rate, most of these studies consider just random value for a strain rate. However, we know that strain rate is a parameter that is going to affect the results considerably in terms of both magnitude of strength and in terms of behavior. At a faster rate, behavior is more like a brittle type. We're going to have higher strength for the specimen, and the strain at failure is going to be larger. However, at lower rate, behavior is more like a ductile behavior. We're going to have a lower strength, and strain at failure is going to be smaller. So it's important to consider to use a strain rate mimicking the conditions we have in the field for testing. And then in most of these tests, they usually miss the effect of tensile strength on the response, tensile strength of the CIs. Some studies say that tensile strength doesn't have effect, but some studies show that tensile strength is going to change the response of the CIs, the behavior of it. For higher tensile strengths, we're going to have a behavior more toward the brittle type. And for lower tensile strengths, we're going to have a behavior more like a ductile type. So all of this, if not considered in simulations, the results we're going to get from simulations are going to be just for a special case. And if when you're trying to use it for other conditions, then the model is probably failed to capture the response of the CIs. So based on this, we decided to develop the objectives of this research. First, by performing a parametric study to understand the effect of different parameters, especially the effect of tensile strength, angularity and friction angle, particle arrangement, strain rate, and confinement. And then by understanding these effects provide a standard procedure for calibrating CIS models. Here, at this part of the study, we decided to develop a model and do these simulations for this parametric study. The model configuration we considered for a simulation, you can see it here. It's similar to what G et al. Were considered for the study. Particles have a diameter of 1.9 centimeter arranged hexagonally. We have specimens with height of 23 centimeter, length of 10 centimeter, and width of 7.5 centimeter. Tests performed under unconfined compression condition using a strain control approach at a rate of 0.01 meter per second. The model we used for our simulation was different from parallel bond. It's called flat joint, developed by Patyandi in 2012-13, and with the use of this model, we were able to capture some of deficiencies associated with parallel bond, especially angularity, lack of partial damage of the interface, and stress dependency of strength properties. How we were able to capture them. These flat joint models provide some skirted face at the interface of the two particles. So even after breakage, we have some angularity for the particles. The interface has some elements, as you can see here, and then with those elements, the interface is able to have this partial damage feature. And then the stress dependency was captured by using these types of model for the contact instead of having the constant strength assumption we had for parallel bond. The parameters we had for these flat joint models, you can see them here. We had ball density, some stiffness parameters, we have some strength parameters, friction, and then we have this contact gap based on which the program decides which particle is bonded and which one is not. Here you can see the results of our simulations in comparison with G et al., with the results of G et al. In terms of axial stress versus axial strain. You can see from this that we were able to capture their response good. So now that we have the model parameters, the model for the simulations, we started our parametric study. We started with particle arrangement effect. For that one, we chose an arrangement presented here, a random size distribution for the particles with a minimum radius of 0.64 centimeter, maximum radius of 1.04 centimeter. Here you can see the results. It's comparison with the single size case in terms of axial stress versus axial strain. You can see changing the arrangement of the particle is going to change the response. First of all, for the random size distribution case, we are going to have lower strength, and also the behavior is going to be more toward a CP faulting rather than brittle behavior, axial brittle behavior. Here you can then, we started a simulation to see the effect of confinement. For that, we performed a study, a simulation, by applying a constant pressure of 20 kPa isotropically applied to the walls of the chamber. And then we were able to keep that pressure constant through shearing using the servo control mechanism. And here you can see how the results are for the case of confined specimen. In terms of magnitude, so the strength we get for the confined specimen is much larger than what we have for an unconfined specimen. And also the response is going to change from a brittle response more toward a ductile response. Here you can see the effect of a strain rate. We perform simulations using 3 different rates, changing from 0.005 meter per second all the way to 0.05 meter per second. And for this simple geometry, you see that strain rate has some effects on the behavior, changing it from axial brittle more towards CP faulting. However, the strength, the magnitude of peak value doesn't change, something we believe is going to change if we go for a more complicated arrangement for the particles. Then here you can see the effect of shear to normal stiffness ratio. And with that, we chose two different ratios, a ratio of 1 and a ratio of 0.5. And as you can see, for a lower ratio, we're going to have lower axial stress at the peak, or shear strength, let's say that, and then we are going to have a behavior more toward a CP faulting. With this observation, we can say that the traditional calibration process, which involves the use of the formability properties and the unconfined compressive strength as the main matching properties, is not going to be the best way for calibration of the model parameters. It's going to fail in considering some of the important problems involved in DM simulations, especially strain rate, confinement, tensile strength, particle size and arrangement, microcracks and internal friction. And we believe that for the sea ice modeling and calibration and iterative process may be needed to find the best set of microparameters. And then I would like to thank you again for listening to my presentation, and I'll be happy to discuss any questions regarding the presentation when we meet. Thank you.